Fibonacci heaps are a powerful data structure, and in this chart we can see why. Now, we've talked about binary heaps, and for them, make heap is constant time. Insertion is logarithmic, which is pretty good. Extracting the min, or getting the min value is constant, and extracting the min is logarithmic. In a Fibonacci heap, we get some savings here in the insertion. So we can insert in constant time, which is great, with everything else being at least as good as the binary heap. And another big gain is our union function is now, if we want to take two heaps and union them together, we can do that in constant time in a Fibonacci heap, which is useful in some applications. Now, we should mention that the constants in Fibonacci heap operations are quite high. And so for small heaps, Fibonacci heaps don't really gain us a whole lot. They do when we get very, very large heaps or heaps with certain properties. So what does a Fibonacci heap look like? This is a Fibonacci heap. This is a figure from the book. We have the min node or the min tree of the Fibonacci heap. And you can see that we have multiple trees. We have a tree here, tree here, tree here, tree here, and a tree here. And at the top we have this collection of rooted trees. And this is called the root list. And you can see why it's called a list if you look at the actual data structures of how these are stored. We have h-min pointing to the min node, and then we have a circular linked list of the nodes pointing to each other. And we have another property where each subtree, or each tree, I guess, is a min heap, or obeys the min heap property. And you can see that in the figure. Here, 24 is the smallest node, and its children are all greater than it. So it has the min heap property. As I mentioned, h-min is the minimum node in the entire heap or the collection of trees. Now, each node, so let's look at, say, 17. It points to its one of its children, and each node also points to its parent. And the children are also in a circular linked list. So the parent need only point to one of its children and then can find all the other children through that circular linked list. That circular double linked list. A couple of other properties each node has. So each node X has a property x dot degree. Oops. X dot degree, which is the number of children that a node has, and it has x dot mark, and that's a property. It's the property of whether the node has lost a child since our parent had changed. And we're actually not going to get that deep into the analysis, but be aware that it's there. Now, we want to know what the costs are of doing the different operations. So these costs in this table. And we're going to use amortized analysis. As we can see here, the binary heap has worst case. But the Fibonacci heap has amortized worst case, which means over n operations, these hold. For any given single operation, it might be more expensive, but if you average out over n operations, we'll get those costs for the operations. So we're going to use the potential method. For our amortized costs. Okay, so we're going to first define a few things. T of h, where h is the heap, T of H is the number of trees in the root list. That's L, list. So the number of nodes in the root list. So there, T of H would be 5. M of H is the number of marked nodes. And the potential function we're going to use is the number of trees in the root list plus 2 times the number of marked nodes. And as I said, we're not going to get deeply into marked nodes, but we need to be aware of that for our potential method analysis. Okay, and we're also going to assume that D of n, which is the max degree of any node, so the maximum number of children any node is going to have, we're going to assume that D of n is bounded in an n heap, an n node heap. It turns out that it's bounded by log n, but for right now, we're just going to assume that it's bounded. So that's an introduction to Fibonacci heaps.